Hi everyone, my name is Patrik Okanovic.
And I'm Grzegorz Kwasniewski.
And today we'll present you our work with the title High Performance Unstructured SpMM Computation using Tensor Cores.
Okay, so science is great. It helps us reveal deep secrets of the universe. It helps us cure diseases with methods unprecedented before. It helps us foresee natural disasters. And, well, for better and for worse, now we have machine learning everywhere. To solve these problems, we built sophisticated simulation algorithms that model how the world works, how the thinking process works. But now, if we want to know the answer, and especially when we get the answer, is a question about the performance. And performance of all these different applications is usually limited by the performance of linear algebra libraries. And one of the most common performance critical kernel is matrix multiplication of various sorts, maybe barred, maybe banded. So basically, if we want to know the answer fast, we need to multiply matrices fast.
And that is ideal for the hardware, which is built around dense matrix multiplication. But are we done?
Well, not quite, because actually appetite grows with eating. So now we want to solve bigger and bigger problems, maybe ask more complicated questions. So what happens is basically our matrices keep on getting bigger. So basically we are reaching the memory limitation and also compute limitation, because these huge dense matrices are sometimes infeasible to compute. So what we sometimes have to rely on is some sort of sparsifying, maybe doing some pruning methods to remove some matrix elements, and maybe actually the problems themselves that we want to solve have some underlying graph structure that cannot be efficiently represented with big dense matrices. So now the question is actually, how do we want to use this hardware that is designed around dense matrices to solve the problems? And our problems are usually unstructured, very sparse, and ill-suited for this hardware.
But we do have solutions, right? Libraries exist. For example, QSparse from NVIDIA and HipSparse from AMD.
Yes, that is true, but actually they are surprisingly underperforming. So, for example, QSparse from NVIDIA, depending on the scenario, can perform several thousand times slower than the achievable peak.
But the hardware also exists. For example, sparse Tensor Cores.
Yes, but I would argue that actually this 2x4 sparsity requirement is not true sparse data structures.
And what about dedicated solutions? For example, DASP, MagicCube, Venom, QSparse LT.
That is true. There is a lot of rated work around, but actually benchmarking them, they still underperform compared to achievable hardware peak, and often they are dedicated to very narrow use cases. For example, they are really crafted around machine learning, and they are not applicable to general problems that are often faced by science.
And our answer to this is SMaT, the contribution of this paper, Sparse Matrix Tensor Core Accelerate. This is the way how we marry hardware for dense matrices with large sparse matrices. So the input we take is a matrix A, which has arbitrary unstructured sparsity, and we input it in the CSR format. First, we create the BCSR format in order to make it hardware-oriented for the internal representation. Why? Because Tensor Cores actually accept tiles, which are basically blocks, and BCSR is ideal for that. So then we perform the reshuffling, pre-processing, in order to minimize the number of blocks. Why? We want to minimize the memory footprint and maximize the compute efficiency. In this example, you can see how this pre-processing reduces the number of blocks by 1.8 times. After that, we input it into our custom CUDA kernel. So, in our custom CUDA kernel, we perform bottom-up to the parallel scheme. Each warp is assigned to a single Tensor Core tile, as you can see on this matrix C. We perform optimizations per warp. The first optimization we perform is skipping empty blocks using BCSR format. Secondly, we perform double buffering and overlap compute with loading. Finally, we utilize the API from Tensor Cores. With all of that, we achieve great results on both sparse matrices and syntactic band matrices, as we will see later.
Okay, so maybe actually SMaT is fast, but let's try to understand why. Let's try to break down this performance, because we introduce a lot of optimizations, but maybe some of them are actually redundant. So is SMaT that fast because of this hardware-friendly format? Or maybe this is because of this efficient pre-processing? Or maybe actually this is irrelevant and the only thing that matters is low-level optimizations? Well, spoiler alert, all of them matter, and let's break down and understand the performance of SPMM kernel. So we model the execution time with this simple linear equation, where the total execution time of the kernel can be brought down to these two main parts. First is the compute time per single BCSR block, so we can think of it as a single unit of computation, just times the number of blocks, plus this constant term that accounts for cache warm-up, kernel initializations, etc. So basically here we see this contribution of these two parts that were previously mentioned. First is this low-level optimization details, so we want to reduce the time per single element. And then the second part, which is this pre-processing high-level optimization, is that we want to reduce the total number of blocks. So now let's focus on the first part. So how can we actually model and improve this low-level optimizations, which is the runtime per single kernel? So here we will test different versions, different layers of optimizations on this plot. So on a y-axis we have time in a log scale, and we will test it on a synthetic band matrices. We chose here for this experiment band matrix because actually if we run it on real CSR matrices, then there is actually a lot of jitter coming from non-determinism in the distribution of blocks. So here the purpose of this benchmark is just to see how efficient we can stream the data from the memory and then how fast we can compute it. So on the x-axis, we will vary the width of the band, starting from almost a diagonal matrix to almost dense matrix. And now we'll see how different performance optimizations impact this runtime.
So we performed the ablation study with the different kernels from the optimizations mentioned before. We start from a naive CSR implementations, and we plot both the model and the measurements. As you can see, the measurements follow the model, and we have reached this by simple linear regression. Note that it is not just a line here, because the scale is actually log scale on the y-axis. With the first optimization using BCSR, we get an improvement up to 2 times compared to the naive baseline. Then, after using Tensor Core API calls, and this is without the BCSR format, we get a speedup up to 12 times compared to the naive baseline. Then, combining both BCSR and Tensor Core API calls, we can get up to 20 times speedup. And finally, using the cooperative shared memory loads, we get up to 22 times speedup. So, to conclude, low-level kernel optimizations are more important than high-level pre-processing. We have noticed that even for optimal matrix permutation, on sparse matrices, we get up to 2.5 times reduction in number of blocks. Yet, we get an improvement over the naive CSR with all of the optimizations up to 22 times. So, we perform our evaluation on 2 types of matrices. First are the synthetic band matrices that go from nearly diagonal to dense matrices. The motivation for that is to isolate performance critical aspects and remove the randomness from the real-world applications. Furthermore, an example is HPCG, where unstructured sparsity kernels are evaluated on structured sparsity matrices. Secondly, we evaluate on the sweet sparse matrix collection, which are large-scale real-world applications, and in the presentation we show 9 representative matrices.
Okay, so now let's see how this pre-processing, reordering impacts these matrices that we evaluate. So let's discuss actually how this reordering works. So we start with a CSR matrix that can be arbitrarily sparsified, and the first step is to create this BCSR format. So this is as simple as just blocking the entries corresponding to actually a Tensor Core API. So in practice, this is 16 by 16. Here I show 2 by 2 to be more readable. So as we can see, if we just do this naive blocking, we are storing all the elements in a block explicitly together with zeros. So it will. So we are risking with actually a lot of zero padding explicitly with that many zeros here. Now, the solution to this is to perform some sort of matrix preprocessing. So here we try to find the optimal row permutation such that if we permute this matrix using this permutation vector, suddenly we can reduce the number of blocks, in this case almost 2 times. Actually, I want to mention that finding the optimal row permutation that minimizes number of blocks is NP hard, so this is out of the scope of this paper to find the efficient heuristics for this problem. So instead, in this work, we actually performed the study on the state-of-the-art solutions. We compared different reordering methods, and from our evaluation, we figured out that Sylos Labini algorithm performed the best in terms of reducing number of blocks in the sweet sparse collection. I will not go into details how this algorithm works. You can find all these details in a relevant paper, but I'll just outline that this is based on max pooling and bit masking that matches the hardware requirements for the Tensor Core fragments, and then performs row reshuffling based on Jacquard similarity coefficient. Okay, so knowing that, now here I want to mention that preprocessing is actually very costly. So quite often finding this permutation is much more costs much more than actually performing SPMM. So we exclude it from our benchmarking time, and we assume that actually if the sparsity structure is known upfront, then this could be in principle performed offline as a preprocessing step, or could be amortized if many, many iterations are performed. Okay, so here what we will be now benchmarking is we start with the original input matrix and we count how many BCSR blocks we have per row. So here we have 3, 4, 3, 3 blocks in each row. Now we will perform our row reordering and count how many BCSR blocks we have, 1, 2, 2, 2. And also we consider another layer where we do row and column permutation. So basically we take our permuted matrix, we transpose it, and we run again this algorithm, so efficiently allowing for permuting both row and columns. This sometimes helps, sometimes actually does not. So for example, in this case, actually we added 1 more block in the last row. Okay, so now what we will be showing is this distribution of BCSR blocks per row as violin plots. So here we actually see this, this average pointed in the middle. And what will be important for the performance, there are 2 aspects. Well, one thing is the less BCSR blocks we have, the better. But also what we will see what impacts the performance is that distribution. So the more variance we have, the more load imbalance we will have, because then some warps will have much more work than the others. So ideally what we want to have for high performance on the GPUs is good load balance, aka we would like to have more or less equal number of BCSR blocks per row.
Okay, so now we show, as Greg said, the number of blocks per row on the y-axis, and we show it for the representative matrices from SpMM. So from the volume plot, we can actually see the distribution of the number of BCSR blocks per row. On the left, we have the linear scale from the representative matrices, yet on the right, we've got the log scale. So we have found their matrices in the SpMM collection that are out of the distribution and need the log scale to show it. We first emphasize the COP20Ka matrix, where with the preprocessing, we can get up to 2.5 times fewer blocks and up to 3 times smaller standard deviation, that is better load balance. Secondly, we emphasize on the matrix DC2, which is a negative example. That is one of the most sparsest matrices in the collection. We see how the coefficient of variation here, which is 10.9, actually hurts the 2D parallel scheme of SMaT. And lastly, we emphasize on the MIP1 matrix, where we reduce the number of blocks for 1.8 times, yet what helps us more is reducing the standard deviation by 8.4 times. So now we show how this affects the performance of SMaT for the respective matrices. For high performance, we want to see small variation, that is good load balance, and a high number of blocks, which is more compute bound. For low performance, that will be for high variation and for a lower number of blocks. So what we can see here is for, as mentioned previously, for MIP, which has got a smaller standard deviation and it boosts up the performance. For DC2, as a negative example, we see that preprocessing does not help the execution of SMaT. For fairness, we have performed these for the respective state-of-the-art methods. We can see for MagicCube that the preprocessing also help. The reason for that is that MagicCube also uses the BCSR format, yet for example for DASP and for cuSparse, the preprocessing actually does not help. The reason for that is that their performance is not proportional to the number of BCSR blocks. So now we ablate on the synthetic matrices as mentioned before. We take in the band matrix with 16,000 rows and 16,000 columns and multiply it with a tall dense matrix. First, we will multiply it with a tall dense matrix with 8 columns. On the x-axis, as previously, we iterate from a nearly diagonal matrix to a dense matrix. And we ask ourselves the question, at what sparsity threshold can a sparse library outperform a highly optimized dense library? So, spoiler alert, we are actually comparing to cuBLAS, which is NVIDIA's library for dense matrix multiplication. Previously, in the literature, the sparsity level for that was around 90–95%, and we'll see what we get. We also plot the A100 peak. In the plot, the red line is SMaT, our contribution, and the black line is cuBLAS, the dense library. So what we observe, firstly, is that at minimum, compared to the second best method, we are always 7 times faster. For the dense case, we observe, compared to cuSparse, we are 1,700 times faster, and we are only 2.3 times slower than cuBLAS. Yet cuBLAS is 33 times slower than the harder peak. The reason for that is because of the dense matrix that has only 8 columns. And to answer the previously asked question, we notice the intersection of red line and the black line, that is SMaT and cuBLAS. And we see that SMaT is faster than cuBLAS for sparsities larger than 78%. As mentioned previously, it was around 90–95%. Now we perform the same experiment, yet with a larger number of columns in the dense matrix. And that is here 128. So firstly, we see that cuBLAS is now 2 times slower than the harder peak, SMaT is 15 times slower than cuBLAS, and SMaT is 2,400 times faster than cuSparse for the dense case. At minimum, it is 5.3 times faster than the second best method, which is MagiCube in this situation. And regarding the intersection point, SMaT is faster than cuBLAS for sparsity levels higher than 96%. Finally, we arrived to the sweet sparse performance comparison on real-world matrices. So, what we notice is that SMaT continuously outperforms other state-of-the-art methods. For example, for MIP1 matrix, SMaT is 125 times faster than cuSparse and 7.3 times faster than the second best method, which is DASP in this case. As emphasized previously, that is the importance of good preprocessing for this matrix. We also emphasized on a matrix with bad load balance, and that is DC2. And the reason for that is it is ill-suited for SMaT's execution model with 2D parallel scheme. So, on average, we are compared to DASP 2.6 times faster, up to 7.3 times. Compared to cuSparse, SMaT is 16.3 times faster and up to 125 times faster. And compared to MagiCube, SMaT is 10.7 times faster and up to 51 times faster. On average, SMaT is better 7.7 times than the respective baselines.
Okay, so to conclude, in this work we presented how we can understand the performance of a critical SPMM kernel by creating this performance model and understanding the impact of both low-level optimizations and high-level preprocessing. Then we use this insight that we built to optimize the performance, conducting our custom CUDA kernel that combines all these lessons learned and optimizations, as well as use efficient preprocessing that leverages the hardware characteristics of modern GPUs. And finally, we wrap it around in one package that is called SMaT that inputs arbitrary sparse matrix in a CSR format, performs all these optimizations, and delivers performance that declassifies all the state-of-the-art libraries. Thank you very much for your attention.
Okay, if you have any questions, please come, instead of raising your hands, please approach the mic and ask the questions. Yes, so go ahead.
Hi, thank you for your great presentation. I was wondering, like, if you have a chart showing the comparisons for the sweet sparse datasets, like how general your method works, like on how many of the matrices you have success.
So we've got additional results, and we had it in a table. We additionally ran across 600 more matrices, which also includes, of course, so small matrices, all different kinds of, and on average across all baselines, it was 3 point something times faster.
And my follow-up question is, have you seen any kind of specific patterns of like subgroups of sweet sparse that your SPMM performs better, like any densities or structural patterns?
Yes, so I would say that it's pattern that is close to synthetic band matrices on which we evaluate is actually a pattern that is good for SMaT. DC2 is a pattern that we emphasize that does not have that good results, and for DC2 you can think it as a chessboard, because chessboard with some distance would have the highest load imbalance.
Thank you.
Okay.
Thank you for the interesting work and interesting talk. Would you please go back to the page that you compare the performance of having different permutations?
Sorry, do you mean
yes,
plot
yes,
or?
Yes, thank you. Yeah. So for these figures, they seems to imply that whether or not doing row or row plus column permutations does not have a stable and consistent impact on the performance. And for some of the matrices, it seems that using the baseline instead of doing any permutation will give us a better performance. So does that imply that using BCSR plus the Tensor Core API will be enough to achieve good performance for SPMM? Thank you.
Yes, thank you for the question. So it is hard to design an algorithm that will always outperform. Like it can be that already the pattern of the matrix is in a format that is very good for SMaT. So what we do is we perform the preprocessing, we reshuffle, and then we see what is the number of blocks. Has it actually been reduced? And if it has, we use it. Otherwise, we stick to the original pattern.
Okay. I understand that you have stressed that you did not take the pre-processing time into consideration, but do you mind sharing approximately how large is the pre-processing time, since the metric you use, the method you use for reordering seems to be costly instead of something very straightforward?
So actually we are lucky enough that on the audience we have the author of the original pre-processing algorithm, so this is Flavio. So if you want, you can talk with him offline, but maybe you want to address.
Yeah, basically the preprocessing is quite costly, so it takes more or less the same time of the matrix multiplication without any optimization. Okay. So which means that if you iterate over your matrix multiplication, the benefit is great. On the other hand, you can optimize and then you can amortize this cost, but this was not the target of this work.
Okay, thank you very much.
But maybe just to answer your question, yes, no, I think that the answer is yes, it is enough to do low-level optimizations, and this pre-processing is, let's say, a cherry on top, but it is not necessary in this case.
Okay, thank you very much.
Okay, let's take a question from this side.
Yeah, I was wondering, you had this 78% barrier that was a lower result than before. I think that was referring to the diagonal bands being dense. Do you have any notion of how that changes if it becomes randomly sparse or sparse in a structured way?
So we didn't perform that detailed benchmarking because then if you want to sparsify the band, then the natural question is, how do you want to sparsify it? Is it random? Because if you do random, then will it be load balance or not? So I think that the indirect answer to your question is this study how the load imbalance seriously impacts the performance. So if you sparsify in a way such that it will be imbalanced, we could see how the performance immediately drops. Yeah. But I'm not sure if this is the answer to your question.
Thanks. It would be interesting to see something like that, yeah.
Okay.
Hi, my answer is also on this similar graph. I'm trying to understand how the cuBLAS's performance is estimated here. So, to my understanding, the two matrices we are multiplying are of the same size, no matter the number of zeros in the matrices. So, cuBLAS that just treats it as a dense matrix should have similar performance for all matrices, because as far as cuBLAS is concerned, it's just the matrix size that dictates the performance. I'm curious why the cuBLAS's performance is not a flat line.
You want to answer? No. Yes, this is an excellent question, and here by performance we actually measure not MNK divided MNK as matrix dimensions, but actually number of non-zeros. So we are actually not counting burned flops of zeros in this case. So basically, even though if we measure the time is constant, the efficient flops drops with a smaller band.
Okay, so it's still, if I assume time is the y-axis, after 78% sparsity pattern, time for SMaT is significantly faster than cuBLAS because it's exploiting the fact that there are so many zeros. Okay, exactly. Thank you so much.
Go ahead.
I have a question on the evaluation. What is the precision are you using? Did you compare it with the FP64?
We have used half precision.
Okay, thank you.
Thank you for the question.
All right, we have one online question. So Magic Cube relies on BCSR as well. Why did you mention that it only operates over a structured sparsity? And two, did you conduct any experiments against Magic Cube in int4 or other data types besides int16?
Yeah, so for the first question was Magic Cube.
Yeah, Magic Cube relies on BCSR as well, so why did you mention that it only operates over structured sparsity?
Magic Cube also operates over unstructured sparsity. Yeah, the Magic Cube was originally developed for machine learning, and what they do is they do not just take random patterns from sweet sparse, they actually use real matrices from transformer models, and they perform magnitude pruning.
Yep.
But maybe actually what we also see in this plot, we didn't emphasize it, but you can see that Magic Cube line actually ends pretty abruptly at the beginning, and this is this problem that we mentioned, that Magic Cube really doesn't scale for very large matrices, so it runs out of memory.
Yep. And the second question was, did you conduct any experiments against Magic Cube in int4 or other data types besides int16?
We have performed using only half precision on Tensor Cores.
Okay. All right. So yeah, let's thank the speakers again. Thank you.